My name is John Verhoeven. Uh, I graduated from the University of Michigan in 1962. Took a job at Iowa State University. I taught metallurgy to students in the material science department and did research at the Ames Laboratory of Iowa State University. It's a DOE lab they have there. And in the last few years, maybe the last 10 years of my career at Iowa State, I began working with bladesmiths, and I wrote a book that's popular among them called Steel Metallurgy for, mistake here, the non-metallurgist. Now, what I'm going to talk to you today about is a discovery that I made working with a very talented bladesmith from Florida called Alfred Pendray. Al and I worked together for about 8 years. It took us that long. And we were able to discover how Damascus steel blades were made. Prior to that, that had been a interesting mystery. These swords gained their fame in the West after the Crusades. King Henry the Lionhearted led the Third Crusade in the late 1100s. His army did not obtain their objective, which was to capture Jerusalem. The reason? Muslims had a great general named Saladin. His soldiers had superior swords. They did not break as easily as the Crusaders' swords, and they were sharper. Stories came back that said they could cut a hanky floating in the air. In addition, they had an attractive surface pattern on them. The Crusaders thought the swords were made in Damascus, Syria, and that's why they are called Damascus swords today. Here's a picture of Saladin cutting a scarf in front of Henry that I found on the web. In the, let's say, early 1990s, I met a man named Leo Figel. Leo was a doctor. As a hobby, he had collected Damascus swords. He would travel to India, and he had a fabulous collection, probably better than any museum in the world. In about 91, I think it was, I traveled to Florida, where he lived, and got to see a lot of his blades, and got to meet him. And Leo sent me a glossy photo of this blade. He wrote a book in, I think, 93, showing all his blades. This is one of them. When you look at that upright, it's an inlay made in gold. Tells you that the blade was made by a famous Persian bladesmith named Asad Allah. It also tells you what year. It's very old. 60, 91 to 92. Here's a picture of a glossy photo he sent me of one of his blades. It shows the surface pattern very well of a Wootz Damascus blade. The vertical sections, I'll call on here, are called a Mohammed ladder pattern. The remaining area in between is the general surface pattern of a Wootz Damascus blade, and it is often called a water pattern or a watering pattern. Now here's an explanation of what we know about how these blades were made in India. The English scientists traveled India in the 17th and 18th centuries and watched them make the blades and wrote reports that are in literature, 5 of them. And they show that the Indian smiths took a small ceramic crucible, loaded it up with pieces, iron, wood, and leaves, heated it in a charcoal-fired furnace, which was able to heat it hot enough to melt all that stuff. And then in the bottom of the crucible, when they got all done, they found this ingot, and they named it a Wootz ingot. And Damascus steel swords are often called Wootz Damascus swords or blades to differentiate them from another type of Damascus sword I will discuss later. After the Wootz ingot was removed, it had a shape roughly of a small hockey puck. They would heat it up hot in the forge furnace, and they beat it with hammers. And they would beat it in this direction here, 1, which would cause it to expand in direction 2. Then they would heat it in direction 2, which would cause it to expand in direction 1. They did that alternately, and they were able to expand that little round shape into a long, thin bar. Now, if you visit any knife shop, you will find beautiful patterned steel blades, which are also called Damascus blade, confusingly, because they're made differently. These blades are made by hundreds of smiths around the world, and they display patterns similar to Wootz Damascus blades, but they're made by an entirely different and well-established process called pattern welding. The name pattern welding was first began to be used for them in the 60s. Now, the way they make them is they take bars of alternating layers of 2 different steels, so they have different compositions. That's important. They apply them together, and they hot forge them together. That welds the alternating pieces together, increases the length. After the length gets long, they fold the bar back on itself, and then reforge it again, repeating the process. So the layer spacing doubles on each folding. So it doesn't take long. After several folds, you get a lot of layers. Now, because of different compositions, one light's dark and the other light's white on the surface. And this gives you the pattern that you can see with your eyeball. Pattern welded Damascus blades and Wootz blades both date way back to 5500 AD. The pattern welded blades started being called Damascus blades in recent years. It's important to understand that they are made by a different process. In the late 1800s, it became very popular to make shotguns out of the barrels, out of pattern welded steel. That didn't last too long because sometimes the smith didn't get the layers to forge well together, and these would occasionally blow up. Here's a blade made by a friend of mine named Bill Dosh. You can see the nice patterns on a typical pattern welded blade. Leo Figil, in one of his travels to India, in this case it was Rajasthan, India, right in the middle of the country, acquired about an 8-inch long blade. It was highly corroded, but he thought it might be good because it had a gold inlay at one end, so he gave it to me, and we etched it. And lo and behold, it had one of the best patterns on the surface, and one of the best internal patterns of any blade we've ever looked at. Here's a picture showing cross-section of the internal microstructure after polishing to a bare finish and etching it in a common etch used for steel. It's called nitol. The Ni stands for nitric acid, and the N of it stands for alcohol. Nitol etches steel such that perlite, which is iron matrix with plates of cementite in it, average composition 0.8, etches it black. The other constituent, which is beautifully lined up as well, is iron carbide. It etches white. It is called cementite, composition 6.7% by weight, 75% or 25% by atomic. Here's how I got interested in these blades. A famous bladesmith, metallurgist, named Cyril Stanley Smith, who had been the chief metallurgist of the Manhattan Project where the bomb was developed in the 40s, wrote a 1960 book describing Damascus steel swords. It explained how they became famous after the Crusades and explained the fact that they could no longer be made. So I had read Smith's book in the early 80s. He and another famous metallurgist, Oleg Sherby, at Stanford University, had a debate in the literature. Sherby had proposed an hypothesis for the mechanism causing the banding to form in these Wootz Damascus blades. Smith did not agree with it. After I read their paper, I agreed with Smith that Sherby's hypothesis was probably incorrect. But I did not agree with Smith's reasons. The reason was I had been doing a lot of work on steel solidification. As a result of that, I came up with an alternate hypothesis. Now, at a research university, if you are successful at getting funding for research projects, they will give you a small percentage of the funds, which you put in a pot, and you can use it as you wish. So I had such a pot, and I had equipment in my lab, and began a research project with grad student Larry Jones using the funding to support the project. Now, to understand the project, here's a little metallurgical background that you would need. Steel is an alloy of iron and carbon. After solidifying from the matrix, the steel consists of 4 constituents: austenite, ferrite, cementite, all present as small crystalline grains. Perlite is the 4th constituent. Its grains are different. They contain a mixture of thin plates of cementite in the ferrite matrix. I've given talks at a lot of bladesmith conferences, and my bladesmith friends that I meet there call our 4 constituents the ites, as they all have ite in their name. Now, here is a reproduction of the iron-carbon phase diagram, which I have put colored regions on. It is a map which locates on the vertical axis temperature. So here we are with iron going up and melting at 1638 degrees centigrade, very, very hot. On the horizontal axis, it shows the weight percent carbon going up to iron carbide at 6.7%. Now, the austenite region is red, and you can see that it will dissolve quite a bit of carbon. Go down here, 2%. The ferrite region occurs at lower temperatures, and it is basically pure iron. It could only contain 0.2%, which is shown an exaggeration here. The other four regions are mixtures, they're labeled clearly so you can see what they are. Now I want to show you what a piece of iron looks like when you look at it in the optical microscope. Go to the hardware store, pick up a piece of iron. Say it's 1 inch in diameter. There it is. Polish that surface carefully so that it becomes a mirror finish. Now etch it with nitol. Put it in a reflecting optical microscope. Look at it at 100x, and you'll see this. Here I have designated 5 regions called grains. These are called ferrite. This is all ferrite. Steel is ferrite at room temperature. If the carbon's high enough, it's got perlite in it. But this doesn't have much carbon. You can't see anything but iron. And these are grain boundaries between the 5 grains. What's going on? Well, each one of these grains is different in a way illustrated here for grain 4. Grain 4 has atoms of iron arranged in it on what's called a body-centered cubic lattice. 8 atoms in the 8 corners of each body, and 1 guy here in the middle. Now, in each region of the grains, you've got basically probably billions of these guys lined up in what's called a crystal lattice. If you compare grain 3 and 4 down here, you'll see that the orientation of the lattice switches at the boundary, and that's why you see the boundary. I'll show you that more clearly on the next slide. After after polishing the surface flat and etching, the nitol etch will etch the various grains differently depending on the orientation of the lattice. Some will etch faster and become more deeply etched than others. In an optical microscope, your eye is up here, and the light's being reflected back at you. So in this flat region, everything's white. However, at these edges, you can see the light gets reflected off the side and they look dark. That's why you see them in the optical microscope. This is a more info on that. Here are the 4 ites. Ferrite, austenite, and cementite are all phases. And They're all crystalline materials, and they all add smooth, and they're all white. Here's cementite. It's a phase mixture. Black regions are cementite plates, and the white between them is ferrite. Well, ferrite etches much faster than cementite. I'm sorry. Yeah. So I said that wrong. Let me start over. The black regions are cementite. White regions are ferrite. The ferrite etches much faster than the cementite, and it's obvious why you get more scattering, because these little ferrite guys hang out with these little hairs, and they're very, very fine, as I'll show you on the next slide. This is a slide of a micrograph I got out of a reference. And these little regions called 1, 2, and 3 are individual grains of ferrite, and they etch white and nitrile. At the grain corners, you often get blobs of perlite. And you also get it along some of the grain boundaries. If you look at that region of perlite in an electron microscope, which allows you to magnify it way, way up, you can see what's going on. The white regions are cementite, and the dark regions are the ferrite matrix. These babies are very, very small. This is 2 microns across, so these are less than a tenth of a micron, really small. You cannot see them in an optical microscope at the highest magnification. Now I'm going to explain a little bit about what's going on those crucibles that the Indians used to melt and solidify their ingots. Think about how the heat flows out of a crucible as it cools. It's going this way and this way. So the solid, after the liquid, which is initially probably up here, starts to form, the solid just shrinks in size. It grows like this from the edge with the liquid trapped in the middle. Now think about this little region here. Here it is blown up. Here's the wall of the crucible. It's solid. Here's the liquid. If you look at it from the edge, like we are here, you might think that is a boundary. It's called the solid-liquid interface. You might think that'd be a flat plane. Well, it is in pure metals, pure iron, pure tin, but it is not in virtually all alloys. It consists of arrays of small needle-shaped regions that look like trees and are named after the Greek word for trees, dendrites. So these dendrites are growing in arrays. You can't, if you look at the face from the solidified front, solid interface, from this direction, that's what it looks like. You can see the individual dendrites, and in each individual grain, these guys are all lined up. Now, what I want you to think about is that you have alternating arrays of dendrites and interdendritic regions. I'll be calling those interdendritic and dendritic regions or bands or sheets, and they're lined up. And why? Well, that's because of the crystal structure of the solid that's being formed. Here are 2 dendrites growing up into the liquid. We have liquid up here. Solid iron will not dissolve as much carbon or impurity elements as liquid iron. Hence, as the solid dendrites grow, they eject the carbon and the impurity elements into the interdendritic regions, right here, here, and here. So you end up with interdendritic regions, which are high in impurity levels, and dendrite regions. We call this the primary dendrite spacing. All steels contain low levels of phosphorus. It is an impurity common in steels. The phosphorus atoms segregate between the IR and the DR bands of the dendrites. A guy called Stead, around 1902 or 3, discovered a special etchant. If you etch the steel, Stead's etch, the DRs turn black, IR is white in optical micrographs, and lo and behold, you can see the aligned dendrites beautifully, and you can see all the interdendritic regions also. Notice that when you switch across the green boundary, you get a sharp rotation in the orientation of the alignment, and that's due to the crystal structure of the grains being different in the two grains. Now here's what happens when you forge one of those little ingots down. These little regions I've shown schematically as regions of dendrite sheets and interdendrite sheets. Well, on forging, there's an alignment that occurs due to the fact that you're squashing this thing down to a very, very much smaller size. Now I want to show you something interesting that led me to my hypothesis. Go to a hardware store and purchase a small bar of steel. It'll usually have a composition, this range, 0.2 or so. We call such steel that's been heavily transformed by rolling or forging wrought steel. Now, if you cut a wrought bar containing these low levels of carbon in half, polish it to a mirror finish, etch it with nitrile, and look at it in a microscope, bingo, that's what you see. You see these beautifully aligned bands of ferrite. See all these little grains? Those guys are all little grains of ferrite. And these black guys, they're all grains of perlite. So these are the perlite bands. So the perlite bands consist of cementite grains, 0.8%, ferrite, or almost pure iron grains, little grains, 0.02 carbon. So knowing all that, I came up with the hypothesis. Research in the early 20th century, probably around the 20s, determined the mechanisms for perlite banding, and it turned out to be interesting and complicated and difficult to figure out, but they did it. And I used a similar method to do our research. Upon solidification, impurity elements in the steel segregate between the dendrite regions, the DRs and the IRs, the interdendritic regions. The element manganese is an example of an element that is segregated. It ends up in the DRs and freezing, and on subsequent cooling of the ingot, it causes the ferrite to form first in those DR bands. Now, ferrite, since it's nearly pure iron, it ejects all that carbon into the surrounding bands, And when it gets up high enough, around 0.8 or just a little bit below actually, perlite forms. Those regions are dark, edging. So the net result is this. The initially formed DRs that formed on cooling, that formed on when the dendrites formed, on cooling, end up as white etching bands of ferrite, and the subsequent formed IRs of the dendrites end up as the dark etching bands of perlite. So, knowing this, which is quite fascinating, I made the obvious hypothesis. Because the steel of Damascus Blades contains 1.5% carbon in them, on cooling, one ends up with a mixture of perlite and iron carbide compound cementite. The cementite is an iron carbide, Fe3C, 6.7% carbon. In contrast, the ferrite perlite banded steels only contain low levels of carbon, around 0.2 to 0.4. So they end up as a mixture of perlite and ferrite. So here's what you got to understand. I'm going to show you some background based on that iron carbon phase diagram that I showed you. Here's the white region, the red region where the austenite is on that diagram. And the austenite consists of what we call face-centered cubic iron. In face-centered cubic iron, you have little cubes with iron on the 8 corners and in the 6 faces. The center of the iron of the cube has a void, and so do each of the edges. These voids are called octahedral voids. And the reason is they're surrounded by 8 atoms. Well, if you look at the big picture of this baby, right in here, for instance, there's a void that is surrounded by 4 atoms. That guy's called a tetrahedral void. Now, let's compare the high temperature austenite to the low temperature ferrite. Ferrite is body-centered cubic. Here's the atom distribution. One in the middle, we call him the body-centered atom, and 8 corners. Well, in this structure, the largest voids are the tetrahedral voids. I have not shown the octahedral voids on here, but they're smaller. So we're interested in the largest voids because that's where the carbon will fit in these guys. Now, the takeaway here is that these guys, the tetrahedral voids, are 30% smaller than the octahedral voids, and that accounts for the fact ferrite can only hold 0.02 carbon. Austenite can hold way more, 100 times more. Okay, now think about cooling. When you heat treat a piece of steel, you heat it up into this region, and then you cool. Now consider 2 ranges, less than and greater than 0.8. Less than 0.8, you cross this line, and ferrite starts to form, kicks out the carbon in between it. They retain the austenite in between, starts to rise in carbon composition. Eventually hits 0.8 and you form perlite. So you end up ferrite perlite. Now, over here, above 0.2, sort of the reverse happens. When you cross this line, the stuff that forms is cementite, and it contains a huge amount of carbon. So the region between is deleted in carbon, and it runs down, and you end up with perlite and cementite. And that's what you, and Ferrite and cementite both look white, and pearlite looks black in the optical microscope. Now, here's the rest of my hypothesis. In addition to what we said earlier, chemical analysis of Wootz Damascus blades showed that they have low levels of impurity elements in them. Also, just like the low carbon steels. In addition to manganese, they contain elements like sulfur, phosphorus, and silicon. So my hypothesis is simply this. One or more of these elements must segregate between the IRs and DRs when the dendrites form, cause the pearlite cementite banding that is observed on Damascus swords. So Larry and I made up ingots of steel with the same composition as known for Damascus sword blades. We hot rolled them to blades, didn't have a forging mill, but we found no banding. Bummer. My hypothesis was wrong. And that wasn't the first time that happened. That generally happened. So I thought at first that perhaps the problem was that we had reduced ingots to blade shapes and not by hot rolling, as the Indians had done. We sent an ingot to Wally Yater, a bladesmith out east, and he had the famous bladesmith Bill Moran forge it to a blade. It was a beautiful little blade. I had a pattern on the surface. It was not nearly the same, and the internal microstructure wasn't the same. The microstructure consisted of the two microconstituents, cementite and come on, brain. Austenite and pearlite, cementite and pearlite. But the structure was not the same. Again, hypothesis incorrect. So Wally got me on to a bladesmith in Florida named Alfred Pendray, who I worked with for the next 8 years on this problem. Al was one of the first master bladesmiths of the American Bladesmith Society. He had read Smith's book and had met him in '75 at an international conference in New York, where it was agreed that no one could currently reproduce a Damascus blade. Al had an industrial-sized forge hammer. He had made over 200 attempts to produce blades. He had melted small amounts of iron of various compositions in the blade in small crucibles, forged the resulting ingots to blades, and studied the internal microstructure in his shop with his microscope, hoping to make the aligned bands of pearlite cementite that occur in Wootz Damascus blades. However, few attempts were successful. So, Al came to my lab after making contact with me in 1988. He arrived on a flatbed truck, bringing a small forge hammer, so we could forge rather than roll. And he also had on his truck a small furnace. I'll call it a forging furnace. I'll show you a picture of it in a bit. My personal funds from the Iowa State deal paid for the hammer. I was there for 2 weeks. He charmed all of my colleagues and grad students with his southern drawl and his many stories. After 2 weeks, we began a systematic study. I went to Florida over the next 8 years with various graduate students and equipment to measure the temperature and record it while making blades in Al's shop with his equipment. We systematically added small amounts of third elements to the iron, making up the ingots, searching for a mix that would give us those aligned bands of pearlite cementite in the forged Wootz Damascus Blades. Wootz ingots are high carbon steels. These steels are fairly brittle because of the high carbon and difficult to forge without breaking. Forging is slow. It requires great patience, which Al had, and I do not. Al developed a technique to reduce this brittleness, which I'll describe here. He thermal cycled small ingots 5 to 6 times between high and low temperatures. This causes the high temperature grain sets to cycle between old and new arrays. As the temperature cycles between the transformation temperature of austenite at high temperatures and pearlite at low temperatures. On each cycling of the grains, on each cycling, the grains become finer. And that the brittleness is reduced with finer, smaller grains. So that's how his technique worked. Now here's a picture of him doing it. Here's a picture of one of his small propane fire forged hammers, like the one he brought to Ames. It is fired by combustion of propane and air, and by controlling the ratio of the two, you can keep the level of oxidation in that chamber reducing. That means if you stick a piece of iron in there, it won't oxidize, which is very cool. So the way it works is this. Here's a picture of Al shoving in a piece of, or taking on, I'm not sure which, of one of his small ingots. Here's a picture of one that he has previously set on the ingot to cool on his anvil. So that's how the cycling works. Doing that, he's able to forge and get much better results, not breaking nearly as many ingots. Here he is at his forge. Here's a blade that's almost finished. Around 6 years of frustration, we simply couldn't make it work. We had a breakthrough, and it was due to Al. He went to a ductile iron foundry near his shop. Ductile cast iron requires low levels of the common impurity elements in iron: carbon, manganese, and phosphorus. The foundry uses sorel metal to make their irons. Sorel metal is a byproduct of a process which reduces an iron titanium mineral called ilmenite to titanium oxide, which is used to make paints. So it's a commercially viable process. The byproduct is a 4.5% carbon iron with very low levels of the common impurity elements: carbon, manganese, and phosphorus, used in these ductile iron foundries. So Al made 8 blades. Here's what we found after the first one. Here the blade is with the sorel. Here's a blade made just the day before with no sorel, pure iron. And you can see, bingo, we're getting alignment when the sorel is used. On the next slide, I'm going to show you that the average composition of a native in the blades was measured to be a minuscule value between 0.009 and 0.006. I could hardly believe it, that such a small amount could cause such a large effect. But it does. Al and I went to Germany in 1962 to a conference on Damascus steel blades. It was the third time they had this conference. At the conference, we met the curator of a big museum in, I'm pretty sure it was Switzerland, but it might have been Belgium. There was a guy named Zaki who in 1924 was given a set of high-quality Damascus blades collected by a German collector, guy similar to Zaki. He donated them to Zaki for science. Zaki studied them. He cut them up and looked at the surfaces and analyzed the chemical composition using techniques available at the time. So the curator asked us if we wanted them, and of course, Al and I were absolutely delighted. He gave us small pieces of 3 blades, number 7, 9, and 10 in Zaki's paper. We also had the Figuier blade, piece of it, and we also had a blade that belonged to a chemistry professor in the Iowa State Chemistry Department named Adolf Voigt. So Adolf, I was able to talk Adolf into donating the blade to the Material Science Department for scientific study. So we had those 7 blades, those 4 and those 3, and 2 more that I had found. So we took those blades, cut them in pieces after looking at them on the microscope. So we had the internal chemistry, and we also had the microstructure variation of those blades, and also 8 blades that I made. Here is a table showing the variation of the chemical analysis of the blades. Here's the average of Al's 8, and here's the average of the 7 good blades we had from collections. What I want you to notice about this is that most all these elements are pretty much the same, except this void blade is a little different. But they all had patterns, including the void blade. Most of the blades had high carbon. And all the blades except the void blade had vanadium. The void blade looked like an outlier. But notice the high level of manganese. It doesn't show, yeah, right here. It's way higher. And we're pretty sure that's why it shows bands. What is it about vanadium that's going on here? Well, it's an element. This is a little bit wrong. The element vanadium has a symbol V. It forms a carbide, vanadium carbide. There are a bunch of elements similar to vanadium. They're called they're called carbide forming elements. These elements form a very stable compound with carbon, very strong bond, which keeps them from melting to very high temperatures. Now, in steels, when you have vanadium present, it ends up in the iron carbide, and it replaces some of the iron in that baby, and changes it to M3C from Fe3C, where M is now a mixture of the 2 elements. Now, when we heat a steel to a high temperature, mixtures of M3C will not dissolve into the iron as much as the pure Fe3 carbides. This interesting fact explains why later experiments show this. Just a tiny bit of vanadium produces the huge effect that we found. Now I want to show you on the next couple of slides, what these carbides do in steels. In 1993, working with a grad student named Paul Berkey, we made a critical experiment. Here's background info you need to understand the significance of this thing. Here's the iron carbon phase diagram with the red austenite in the, up here and blue fairy down there. Now, take a piece of steel, heat it up into this range, and then cool it slowly, like in an ingot. Over here, if the percent carbon is below 0.8, you'll get ferrite and pearlite forming, and over here you'll get cementite and pearlite. Why? Well, think about what's going on. If you go from over here, the austenite will cross this line, start to form high purity ferrite. That'll cause the remaining austenite to increase, and it'll eventually increase to the point where pearlite forms. Over here, however, above 0.8, just opposite happens. When you cross the line, the first stuff to form is this cementite, and it contains a ton of carbon. So that means the remaining region drops. It drops down. Then you end up with pearlite and cementite. Okay? Now, suppose that instead of slow cooling, you quench. This changes the big picture completely. Quenching does not allow enough time for the carbon to redistribute itself when you cross down to temperatures of about, actually it should be a little lower than that. Martensite starts to form, usually down around here. So if you quench fast enough, you'll get martensite forming down there. And before the surroundings of the areas have time to reach percent carbon, it transforms into this new crystal structure called martensite. It's actually body-centered, but it is not body-cubic. It's body-centered tetragonal. One of the axes is longer. And the structure is highly strained and extremely hard. Steel containing martensite is the strongest useful metal. It was discovered by our ancestors way back when they first learned how to make iron, 1000 BC. In the microscope, martensite appears black in the optical microscope. At percent carbon levels up to 0.6, it has a lath shape, but it transforms to a plate shape as percent carbon rises. And at around 1%, some of the retained austenite is retained. And you can now see the plates as shown here when you have 1.4%. Because the retained austenite etches white and the plates pop out at you. So here we are at 0.8 to 9, and we have a mixed structure of plate and lath. Over here at 1.2, where we've increased it, it's mostly all the plates. They look like fuzzy things. But when the retained austenite appears, it sharpens the boundary, and you can see them clearly. Now, up here I have listed the Rockwell hardness of the various martensites. And notice how hard they are. The hardest is the lower carbon, 0.8 to 9. At 0.4, it's still around 60. And at 1.2, it's dropped to 63, and at 1.4, it's dropped to 61 due to all this retained austenite. Now, I want to point out that steel is amazingly strong. The strongest competing titanium or copper alloy has a maximum hardness way down, up around 44. Now, here's a description of a critical experiment done by Paul in 1993. We took a piece of fig blade, heated it to 1050 for 3 minutes, and that's what it looked like after we quenched it in water. The bands were all gone, and we're just left with that marked set structure. We then forged it between 820 and 680 6 times, once with forging during the time 6 cycles, and once with no forging. And this is what we find. The bands come back magically. This uses cementite etch, so the bands look black on a white matrix. What's going on here, we think? Well, the vanadium atoms do not migrate by diffusion at 940. Hence, their banded distribution remains. And on subsequent thermal cycles, somehow those bands of vanadium cause the pearlite cementite bands to form. So, we took a piece of the fig blade and heated it for 18 hours at 1200 centigrade. Now, this severe heating produced a huge change. After the 6 cycles, which we did following the heating, bingo, all the bands are gone. Cementite appeared as black little particles in a white matrix of pearlite after we used that etch. We think what's going on is that the much higher heat of 1200 has homogenized the vanadium particles, because at 1200 degrees they will diffuse much faster and can homogenize. And that's been shown by experiments to happen. Paul repeated those experiments using a piece of both the fig blade and a couple of Al's blades that displayed good banding. We put a thermocouple in so we could measure the temperature variation, and that was the result. The results were the same on both blades. The bands of pearlite, cementite had returned after the 6 cycles, and had the same spacing as original. The results show two important, say it again. The results of these experiments are important for 2 reasons. First, they showed that the important factor in causing banding in Wootz Damascus Blades is the same as that factor causing banding in raw carbon steels, as microsegregated nuclear elements between the dendrites formed on slow cooling. We know this because the 1920 guys had proven that the cause of the banding was the distribution of the, I think, the manganese and the phosphorus. They had shown it went away by high temperature annealing, and the banding went away. Same deal. The second interesting result that this shows is Shirley's hypothesis could not cause Wootz banding because it would not allow the bands to form after being destroyed and then thermal cycle. Now here is an explanation of what I think is going on. I've shown here the distribution of the 2 types of carbide after 1 thermal cycle. So after 1 thermal cycle, because of the dendritic solidification, you'd have M3C over here, and over here you would just have plain old Fe3C, because that's pure iron freezing over there in the dendrite regions. Okay, so we heat that baby up, and what happens is that These guys, not having vanadium in them, will dissolve into the austenite much faster. So after a few cycles, this gets bigger and that gets smaller. After a whole mess of cycles, you see these guys lined up and pretty much nothing left over here. Now this interesting mechanism would account for a main difference in Wootz banded blades and rock blades. Why? Well, rock blades don't require any cycling. They form in a single cooldown, but not with these guys. You've got to throw a cycle, or you won't see them. After one cycle, you don't see them. That's how come my initial hypothesis failed. I didn't cycle it, and I didn't have the right junk in there anyway. Even if I cycled it, it wouldn't have worked because I didn't have the vanadium in there. Here's a bar graph showing the melting point of the various carbide forming elements. And what I want you to see is that they have extremely high melting temperatures. 4,000 degrees centigrade. It's really hot. Hafnium carbide and tantalum carbide have the highest melting binary compounds known on the planet. That illustrates the stability of carbides. Here is vanadium carbide. Melts at 2810 centigrade. That is 5090 F. Al and I did a study where I brought small pieces of iron doped with these carbides. He made blades out of them of various compositions. We looked at the blades after we etched and cut them and etched them, and analyzed the intensity of the banding, and we found the strongest banding occurred with vanadium and moly, molybdenum, chrome, nickel, niobium, and manganese all gave weaker banding at these composition levels. At 01, chrome didn't band. Okay, so now I'm going to conclude. The mechanism causing the aligned band formation of perlite banding, cementite banding in Wootz Damascus blades is similar to that causing perlite ferrite banding in rock, low iron, carbon steels. Both results from the segregation of the impurity elements between the dendrites and the interdendritic regions formed when the steel solidified slowly, followed by severe deformation of the ingot. However, the Wootz Damascus blades differ because they're higher in carbon, much higher, 1 to 1.8 versus 0.15. Second, the impurity level of the carbide impurity elements necessary to cause the Wootz banding much smaller than impurity elements causing rock. I mean, this guy is only 0.0089 or so, and this guy is 0.1 or so. The perlite, and the third one is that the perlite cementite banding in Wootz Damascus blades requires multiple cooldowns, while that in the rock, low carbon perlite ferrite banding occurs on a single cooldown. And it's quite interesting, I think, to think that how this happens, because you make the Damascus blades by forging, so it automatically happens. So we finished up the work in the 90s, published a couple of papers, one in the Journal Metals in 98 and the other in Scientific American in 01. Later we were contacted by 2 different YouTube authors and made 2 YouTube videos that are available on the web. One's called The Wootz Hunter by Todd Oppenheimer, 15 minutes. The other is longer, Secrets of Wootz Steel by Mike Lawrence, 50 minutes. In 91, Al made this blade, which he gave to me. There's a piece of tape down here that I put on so you wouldn't cut yourself. And on the blade, you can see the Damascus pattern and the rose pattern and the regular pattern in between. We sectioned this baby and made micrographs of the pearlite cementite banding that we found it will pretty well line up. This is what the surface looks like, showing the two types of patterns, the rose and the Mohammed. Now this blade was made before we were aware of the importance of having a carbide forming element. We didn't really know what was in it. It was one of the blades we made with various stuff that Al had. It was made with the wrought iron that he had. He had a chain of wrought iron out his back jump pile. We cut that up and used it. And bingo, it worked. Later analysis of this blade showed us that it did contain 3 carbide forming elements. Chrome, 0.09, moly, 0.09, and enough vanadium also. Well, those guys together I'm sure, are what caused all this beautiful formation to occur when Al made the blade. Now, my last slide show you how these patterns form. There was a debate in the literature on how the Mohammed ladder and the rose patterns were made by these ancient smiths. Al made patterns using both techniques. In both techniques, you make a groove in the surface. In one technique, you cut it with a cutting tool, and the other one, you just smash it in there with a piece of hard stuff, like a piece of iron. Now, here's a picture that shows the aligned bands you're starting with. And I want you to notice that they're at an angle to the surface, so that on the surface there's a distinct spacing as long as the band spacing remains constant. Now, what you do after you make the cut, or you forge it, the cut's not very deep, and you forge it flat. Now think about what happens to those bands. They have to rotate. This band has to line up with that one. So now, when you look at the surface, the edge spacing, the spacing on the surface, becomes very fine at each edge of the cut. So here where he made, let's see, which one did he do the cut on? This one. Here where he made the cut, look how fine they are at the edges. Same way with the rose pattern. Same down here where he made the indent. So anyway, that concludes my discussion of how we figured out how these blades were made. I hope you enjoyed the talk.